and thank you for turning up. I know on Friday afternoon it's easy to just sneak off and have a nap, but I'll try and keep you awake, keep it light and breezy. So this is a talk about the OpenLI project, which is a project that's been occupying me over the last 12 to 18 months. And it's designed to allow internet service providers and network operators to meet their lawful intercept obligations without having to spend a whole lot of money. So what is lawful intercept? Lawful intercept is the legal and authorized interception of telecommunications, and usually that's used with the purpose of either investigating or trying to prevent criminal activities, terrorism, things like that. So it's a power given by the government to law enforcement agencies, such as the police, national security agencies, intelligence services, and so on, to be able to investigate or intercept the communications of a person of interest and use those to try and prevent or investigate, solve crimes. So, of course, nowadays we live in what is primarily a digital age. So the vast majority of everyone's communications are going over the internet in some way, and this includes obviously email, but things like voice over IP, replacing people's landlines in their homes, instant messaging, social media, video calling through services like Skype, and even all of your mobile phone calls are typically carried over the internet for at least some portion of the way. So this means that these old school wiretapping techniques that the agencies used to use don't really apply anymore. So they have to make way for new techniques. So how does lawful intercept in the digital age really work? Well, here's an example. I've got an ISP here. They have 3 customers, Anne, Bella, and Chad. And the ISP effectively acts as a gatekeeper, right? All of the communications from these 3 people going to and from the internet are passing through the ISP. And this means that the ISP is in a perfect spot to covertly intercept the communications of any of those customers. Now, while Anne and Bella are perfectly law-abiding citizens, Chad is a slightly shadier character and has managed to attract the attention of the police. The police would like to intercept Chad's communications to gain some additional evidence that could prove he has partaken in the crime that they believe that he is involved with. And so the police must obtain a warrant for an intercept of Chad's communications from a judge. Now, assuming the police case is reasonable, then the warrant gets issued and the police then forward that warrant on to the internet service provider. Now, by law, as a result of that warrant turning up, the internet service provider must forward a copy of all of Chad's communications that pass through their network onto the police for as long as that warrant remains in effect. But the ISP also has a few additional obligations that they must fulfill when performing such a lawful intercept. So the most important one, perhaps, is that Chad must not be able to detect that he is the subject of an intercept at any time. Otherwise, he's obviously going to stop doing the things that might incriminate him, right? And this can range from the very obvious things that the ISP shouldn't do, like suddenly disconnect Chad and reconnect him on the magic interception link, through to things like degrading. There can't be any degradation in Chad's internet performance. There can't be any changes in the routes that Chad would normally use to access the internet that could be detected with a tool like traceroute. There can't be any increases or decreases in latency that he might recognize if he was technically savvy, and so on. The infrastructure that the ISP is going to use to perform the intercepts is an obvious privacy concern, and so they have to take great pains to prevent any unauthorized access to that system. And that includes from other employees at the ISP, right? So nobody else other than the people who are authorized to be involved in conducting the intercepts should be able to see that an intercept is taking place, right? So imagine if Chad had a friend who worked at the ISP, and this ISP had a big dashboard that they had on a big monitor somewhere that was listing all the current active intercepts. Chad's friend might tell him that he is under surveillance. The ISP must be extremely careful not to over-collect, and by over-collect I mean they can't collect any traffic or any communications for any people other than whom the warrant applies to. So Anne and Bella's traffic must remain private. But on the flip side of that, failing to intercept all of Chad's communications is also a very bad thing, right? So consider an example sentence that say that it was intercepted and it's being replayed in court, where Chad appears to say, I will help you with robbing the bank. Looks like Chad might be guilty, but what if the intercept had accidentally missed the part of the communication that contained the keyword not, right? So Chad's not so guilty looking now. And even if there is some possibility in the collection mechanism that under collection could have taken place and not been detected, that's enough for a savvy defense lawyer to be able to raise any reasonable doubt about the value of the intercept as a whole. So what is the situation like in New Zealand for LI? So it's governed by, at the moment, a law called the Telecommunications Interception Capability and Security Act, more affectionately known as TICSA. So this was passed in 2013, and the key part of this is that all internet providers in New Zealand must be LI capable if they have 4,000 or more customers. And by LI capable, I mean they must be able to, not quite immediately, but as soon as is reasonably possible, begin intercepting a customer's traffic on demand and delivering that to a law enforcement agency. Of course, in a wonderful example of the separation between law and actual practicality, the implementation of this was not included in the definition that was going to be announced later. So this question was resolved through an announcement in the New Zealand Gazette, August 2017, and this is where the ETSI standards for LI were first mentioned within the context of New Zealand Lawful Intercept. There's two problems with this. The first one is that the Gazette is not exactly a required reading for any New Zealand network operators. And the second one is that most operators had probably barely even heard of the ETSI standards before this time. So this was all very new. So what am I referring to when I'm talking about the ETSI standards? So ETSI is the European Telecommunications Standard Institute. They are an organization, say, similar to the ITU and various other standards bodies. Would like to sit around and have meetings and come up with the way that things should work without ever thinking about how you would go about implementing them. Their standards for LI are very widely adopted throughout the world. So Europe, obviously, many countries in Asia are using them, New Zealand, obviously now, and also Australia are looking at this as well. The one exception, of course, are our good friends in the US who decided to come up with an entirely separate mechanism, but the underlying principles are more or less the same. So what do these standards offer that make them so appealing? So first off, they are very comprehensive. There's a set of standards that cover all of the different modern digital technologies for communication. So you've got standards for conventional internet traffic for IP. You've got a separate standard for voice over IP. You've got a standard that covers the interception of email, mobile communications, and so on. But this does also introduce a bit of a downside in that there are a lot of standards to read through. They are lengthy, they are complex, they refer to each other all over the place, and that creates a significant barrier to entry for anyone who's thinking about implementing them. So the key requirement in the ETSI LI standards is that intercepted traffic must be streamed live in real time to the law enforcement agencies over an internet connection or a network connection of some form. So this gives the agencies a chance to react to the information that they're receiving as it happens. So consider the case, for instance, if there is an ongoing kidnapping investigation and the kidnappers are talking about where they're going to transfer the person they've kidnapped to, the police would like to know about that, say, within 5 minutes of that discussion and not the next day. When you have for the relatively low security intercepts, so a lot of police investigations would fall in this relatively low security category. Those would be streamed using TCP sessions over the public internet, but wrapped in some form of encrypted tunnel. Higher security intercepts that involve intelligence agencies, spies, so on and so forth, they'll have additional security requirements on top of that. Each ETSI intercept is delivered using two separate handovers. So they have a handover for delivering what's called intercept-related information, IRIs. This is mostly metadata about the intercept. So it will tell them when a target authenticated with the ISP, when they were assigned an IP address and what IP address they were assigned. In the case of a voice call, it's when was the call initiated, who initiated the call, when it was accepted, things like that. And then alongside that, you have the communication content itself, which is the raw data packets that the communication took place in. So these are two separate streams of information. They're often used to corroborate each other. ETSI is very rigorous about ensuring that every intercepted packet is properly labeled. So all traffic for a particular intercept is labeled with what we call an LI ID or an intercept ID, and that's assigned by the agency that is requesting the intercept. And then each separate voice call or IP session within an intercept has its own unique communication identifier on top of that. And then finally, within each communication, everything's tagged with a sequence number. So you can make sure that everything's in the right order, and you can tell if anything's gone missing between the point of interception and the law enforcement agency that's receiving it. So as you can see, LI is a little bit more complicated than just TCP dumping an interface and uploading that pcap file to some FTP server somewhere. But there is one big practical issue with this choice of the ETSI standards, and that is the issue of money. So in the New Zealand case, the network operators get absolutely no financial assistance to cover the costs of integrating LI into the networks. And when we're looking at the typical vendor solutions for LI that are ETSI compatible, the costs are running into the tens, if not hundreds of thousands of dollars. And that's not even taking into account the ongoing licensing costs that come along with that. Unfortunately, the option of not complying is just as, if not more expensive. So operators that are found to be non-compliant when they are called on to do an intercept, they face a daily fine of up to $50,000 per day. And so shortly after that announcement in the Gazette that the ETSI standards were required, you don't need to read all of this email, but Dave Mill raised this subject on the New Zealand Network Operators Group mailing list. And he had noticed that there was no open source solution for LI. And he was curious as to what other operators in the same position as him, smaller operators in particular, were doing about meeting their LI requirements. And the answer was nothing. It soon became apparent that very few operators were even aware of the new requirements. Remember, I said that the Gazette is not exactly a widely read publication, and so they had made no effort towards meeting them. And there was now an increasing realization within that community that they had a big problem on their hands with no obvious solution, right? How are they going to be able to become compliant without going bust? And that's where I came in, or my research group came in. So some of the operators in that group approached us at the One Network Research Group. We're at the University of Waikato in Hamilton, and they asked us if we'd be able to help out. And why did they come to us? Well, we have a bit of a history of doing stuff with capturing packets. So we've published plenty of research in the past based on live packet capture analysis, doing this stuff in real time. And we'd accumulated a bit of expertise in this particular field. And the operators figured that might be quite helpful in this situation. Furthermore, we've been quite closely tied with the operator community. We show up at their annual conference every year, which happens to be next week. And so we like to think we're fairly well regarded within the industry. And so right from the outset, the suggestion was for us to develop an open source LI solution for New Zealand network operators. Right, so the operators themselves were really good about this. They were quite keen for the software to be open source, to be available. A lot of what WAND has done in terms of our research outputs and our software has been released in the past as open source. So it was kind of a natural fit for us to do it this way. And so from this, we kind of, this OpenLI project was created with the idea of it being a solution that was built by the network operator community and ourselves as friends or members of that community for the mutual benefit. So that being said, there would still be some costs that associated with this project that we'd have to recover somehow, right? So this was a big project. It was a serious project, required a real commitment of not just time, but also expertise, right? This wasn't something that we could just fob off to an undergraduate student to do as their honours project, or just knock it out in a few spare hours that we had. So this was going to be a job for someone who at least had a bit of experience in doing this sort of thing, and so that's how it fell into my lap. So I personally, I'm a research programmer. I've been with the group for a long time, over a decade, and most of that time has been spent writing this packet capture software for the research projects we do. So it became my problem. It was also quite important that the project was treated as a priority, right? So already at this point, the ISPs were under quite a bit of pressure to be LI capable as soon as possible. So they couldn't really afford to wait, years for me to get around to churning this out in my spare time. So we decided to go back to the community, and we said, right, we're willing to do this, right? But we're going to need a bit of money to justify me taking time away from my other projects to do this. Excuse me. And so, like I say, those funds would be used to basically cover the cost of me spending around half my working hours on this project for as long as the fund had money in it. And in the end, that turned out to be about a year. So we figured a good minimum contribution would be about $10,000. And that's, based on what I said earlier, that's a tiny fraction of what each ISP would have been looking at to buy a solution, or of course a tiny fraction of the fines that they'd be looking at paying if they were caught out. But when you propose a solution like that, there is always the danger that we'd get a bit of a prisoner's dilemma and not enough operators would contribute. Because as you can imagine, there's the obvious route of you go, well, if I don't pay now and my competitors all do, and it's going to be open source at the end, then I can just get it for free, right? So we tried to throw in a few incentives to encourage people to get on board early. So anyone who provided funds for our project was given pre-release access to the code, so they could get a head start on trying to integrate it into their test beds, and then possibly even towards production by the time the code was actually ready. And we also gave them a real direct line to myself in terms of getting assistance and getting help, support with playing with that pre-release code. We also gave them a bit of an opportunity to request certain custom features that might be necessary to make the software integrate properly into their network. So everyone's network is different. There are lots of fiddly little things that maybe that I wouldn't have necessarily thought of when coming up with a generalized solution. And so if you were on board with us and you wanted something custom, I was going to do it for you as part of my development. And so we had some really cool companies come on board. Some members of those companies happen to be in this room today. So I'll just remind you that those companies are great and you should thank them a lot for what they've done. So they stepped up, helped fund the project, and it was full steam ahead. So let's talk a bit about the software itself. So like any good software project, OpenLI is built on top of a lot of other people's work, and we should probably acknowledge that work. So the most obvious one, given that I'm talking here today right now, is Linux. So OpenLI is specifically written for Linux. I developed it and tested it mostly on Debian because that's what we use at WAND. So I know it works pretty well there, but there's no reason why OpenLI shouldn't be able to be easily used on other Linux distros as well. Everything's written in C. There's two main reasons for that. One is that C is still really the only option for anyone trying to write any serious packet capture and analysis code that wants to perform at even a decent rate. And the other reason is that I'm actually still an old school programmer. I like writing C code, so that's what I used. Another key building block, the libtrace packet capture and processing library. So this is code that has been developed and maintained by Wand, and a lot of it by myself over the last sort of 10 to 15 years. The main aim of libtrace is to simplify the task of writing packet capture code by hiding a lot of the variations and the nuances of different packet capture formats and different protocol stacks and different ways that you can layer protocols on top of one another. What we've done is we've kind of abstracted a lot of that away and put it in a standardized API. And so you write one simple libtrace program, and it works regardless of how many VLAN tags you've got on your packets. It works regardless of what capture format you use to capture it, whether you use pcap, whether you use a Linux socket, so on and so forth. So libtrace is really cool. And if you do any work with pcaps, packet capture, TCP dump, traffic analysis in general, definitely encourage you to look it up. One of the capture methods that's supported by libtrace is the data plane development kit, or DPDK. So this is a collection of drivers, libraries that can be used to perform very high-speed packet capture using relatively inexpensive commodity network interface cards. It was originally a project that came out of Intel, but for use mainly with their own 10 gigabit cards, but it's spun off into its own open source community now. So it's really quite helpful. The last thing I'd like to mention is this library, libwandr. It's a general purpose library that I wrote for encoding and decoding messages using DER, which is the format that we needed to encode our ETSI output in. So I wrote it with it was specifically written for OpenLI, but the API was generic enough that it can be used outside of that as well. So it's its own separate LGPL entity now. So the software itself, so it consists of three distinct components. So the first one's the provisioner. This is basically acting as a centralized manager for the rest of the OpenLI system. So what you generally have with the provisioner is you have the police, they issue the warrant to a very stressed-looking network operator, and all they have to do is just take the intercept details and enter them into the provisioner as configuration. So the provisioner is the only part of the OpenLI system that the operator would have to interact with on a regular basis. Right? The other stuff can kind of just sit there, and maybe a sysadmin might log into it every now and again to make sure it's still there, but otherwise the operator is really only dealing with the provisioner. Most of the time it's got very little work to do because presumably you're not being requested to do intercepts every day. And so it's perfectly suited to maybe running in a VM or as a process on the same box as a whole bunch of your other management or monitoring systems. At the moment, all the configuration for intercepts is manual. So they sit in a config file. If you want to add another one, you edit the file, and then you tell the provisioner service to reload its config. But we are thinking about ways that we can improve that. The second component is the collector. So this is the real workhorse of the system. So the network operator would provide the collector with a feed of the network traffic that could be subject to an intercept, usually by configuring some sort of mirror port on the appropriate device in their network. The collector also receives a set of intercept instructions from the provisioner. So those instructions would tell it who is an intercept target and what metadata should be included in anything that's encapsulating those records. So that lawful intercept ID, for instance, that I mentioned earlier. So each packet that comes in from the mirror port will be checked to see if it's related to an active intercept. If so, we'll take a copy of it, wrap it in the appropriate encoding, and then forward it on to the last component, which is the mediator. Now, because the collector will have, or could have, a very heavy workload, we do strongly recommend that this is run on bare metal, some real physical hardware. VMs simply aren't suitable for the high-speed, reliable packet capture that you're going to need to be able to do for LI. Having said that, though, we've tried to keep the hardware requirements pretty modest. So you sort of off-the-shelf pizza box 1U server from whichever vendor you prefer should be more than enough. With the one addition of a DPDK capable 10 gig network interface card, and that's just so that if you throw a lot of traffic at it, it'll be able to keep up. And even these NICs aren't that expensive these days. So the mediator is the last component, and really all it does is it collects together everything that the collector or collectors throw at it and make sure that it's forwarded on to the appropriate law enforcement agency. The provisioner issues these forwarding instructions to tell the mediator which intercepts go to which agency, so everything ends up in the right place. The mediator is the only component that will need any access outside of your network, so everything else would be quite internal to the core network, and the mediator just talks out. Even then, it's only making outgoing connections over the encrypted tunnel that hopefully you've been able to configure with your agencies earlier, so something like IPsec or a VPN or something like that. The mediator actually attempts to keep those connections up at all times. So it's using regular keep alives both at the TCP layer and within the mediator protocol itself to monitor whether it can still reach the agencies and give you an opportunity to repair that connection if it goes down before you need to send them an intercept. And of course, since ISPs may have multiple points of presence where they would want to put these interception boxes, for instance, you might want to put one in every major city. The OpenLI architecture was designed from the ground up to support multiple of these collection boxes. Right, so in the time that I've got left, I just want to go over a couple of the big picture issues that we ran into. So the first challenge, which hopefully is reasonably obvious to anyone who has any experience in networking, is that while the agency might turn up and request that we intercept traffic for Chad, few, if any, of Chad's communications are going to have his name in them, right? The packets don't have an envelope surrounding them saying from Chad or to Chad or anything like that. So the ISP itself might have assigned a particular username to Chad, and that'll be used within their internal authentication system, but even then that's not something that we might necessarily see in the communication stream itself. So what we really need is we need to know what public IP address Chad is using, but we also have that issue that IP address is often assigned dynamically, so there's not necessarily a fixed record that we can go, okay, Chad maps directly to this one address. And Chad's not guaranteed to keep that same address for the duration of the intercept. If Chad turns off his home router for a couple hours, turns it back on, you might get a new address. And so we've got to keep track of any changes like that. When we're doing intercepts for voice calls, this is even trickier because we need to know the UDP port numbers that the voice stream is going to be going over to be able to cherry pick just that media out for the intercept. So of course, in practice, what happens within ISP networks is that we have these special control protocols that are used to announce or negotiate these sorts of details. So if you have an IP session, the most common protocol that's used for this purpose might be something like Radius, and that's used to announce a user will authenticate through Radius and then get back an IP address that they can use for the duration of that session. In the VoIP environment, SIP is the protocol used to establish the phone call, and as part of this establishment, there's an exchange of IP addresses and port numbers that the media stream is going to appear on. So as long as we're given access to the packets that make up these control protocols, and we are able to parse them, then we can ask the ISP to give us a feed of that, pass those control messages into the collector alongside the real communications, and then the collector can inspect those and use that information to work out which traffic actually maps to Chad's current IP sessions or his currently active voice calls just by looking at the packet headers, pulling out the IP addresses and port numbers. these control protocol messages are also used to form the basis of that IRI metadata I mentioned earlier. So there's a lot of direct one-to-one mapping between the messages in those protocols and the metadata that we're required to intercept anyway. So we have to have them regardless. But there are some complications. Radius is not too bad. Radius is a protocol that's generally entirely internal to that ISP, and so it's reasonably trustworthy. Any names that are announced in that protocol, we can assume are actually going to be the names of the person that's making that request. But SIP is a bit trickier to work with. In particular, SIP has a couple of fields in it. That has a from field and a to field that normally contain a name or a phone number of the person who is either making or receiving the call. But it turns out that the from field is quite easily spoofable. So Chad could quite easily replace the from field with someone else's name. Or even worse, someone else could accidentally end up replacing their from field with Chad's name, and then we get the overcollection problem again. But it's also possible for incoming callers to suppress their caller ID. And so the agency may not be able to see who's calling Chad, and that is obviously information that they'd be quite keen to have. Fortunately, there are a lot of places in the SIP header where we can find this information. We have to be a bit trickier about it, but there are other headers that we can use. And it also does somewhat depend on whether we receive our SIP feed from either outside the SIP server, inside the SIP server, and things like that. Some headers tend to be stripped, or some fields tend to be stripped. And so if you're on the wrong side, then you might miss them again anyway. The other problem is that in New Zealand, we actually have pretty good internet. So in my home, in a town of about 10,000 people, I have a 1 gigabit plan at home. And I'm sure plenty of the other New Zealanders in the audience have something similar, right? So this creates a bit of a problem if you're thinking about intercepting people's traffic, because all of a sudden you might have to deal with a simultaneous intercept involving multiple of these people, all who happen to be saturating their 1 gigabit per second plan, right? And if they are doing that, how can we be sure that we can intercept all of that traffic without dropping any packets due to poor software performance, right? So we've got to make sure that our software is working at the optimum speed, not wasting even a nanosecond of processing time just for that worst case scenario, right? We can't afford to spend any time unnecessarily looking at packets. So one of the big advantages that we get out of using libtrace is that we're able to spread our capture workload across multiple CPU cores basically transparently. So what this means is that we can do multiple simultaneous captures on different interfaces. So the operator can spread some of the load themselves by plugging in multiple interfaces, different feeds of different classes of traffic. We can assign multiple processing threads to each of those capture interfaces. And we can also, automatically get support for a variety of high-speed packet capture methods. So this can include things like DPDK, as I mentioned before. That's natively built into libtrace. If you've got a bit more money to spend and you have, you definitely need some high-speed stuff, then it'll work very well with the Endace passive capture hardware. And if you have neither of those, then you can still fall back to the tpacket interface within Linux itself to get some degree of parallelism. But this introduces a whole new set of problems, right? Because if we start spreading packets all across multiple threads, how do we sort of synchronize that state? How do we keep track of things like if I have a SIP session that's announcing the details of the call appearing on this thread here and the media stream appearing on this thread over here, how do I make sure that this thread knows the port numbers that it should be looking for to perform the intercept? And so, and another similar problem is we have to keep these sequence numbers very consistent for everything that we're exporting, right? And if we're intercepting half of someone's IP session over here and the other half over here, we don't want to be exchanging a lock back and forth to ensure that we are assigning our sequence numbers in the right order. So how do we keep track of that? And the answer is actually more threads. So we had to add a thread that was dedicated to parsing SIP packets. We add a thread that's dedicated to parsing the radius packets. We have a thread that's dedicated specifically to keeping track of sequence numbers. And so there's a reason why I didn't include a diagram of the collector infrastructure itself, because there's so many things being passed back and forth through message queues that it's impossible to draw in 2 dimensions at least what that looks like. We have a pool of worker threads for doing the encoding work, because the encoding is actually the hardest part of the job. It's another problem that I'm not going to mention today because I don't have time. And then finally, we have a forwarding thread at the end that kind of takes all of the output, figures out the right order, reorders it, and then pushes it out to the mediator. And so all of this is sort of, maintained with a whole bunch of 0MQ message queues that are just used as a lockless way to chuck messages around between threads. So having said all of that, we did it. It's done, sort of. It's done. So all the core functionality is in place. We can do IP data intercepts. We can do VoIP intercepts. It seems to work reasonably well. So we've got a successful production deployment with one of our ISP partners, and I'm hoping that a few more will give it a crack in the coming weeks. I'm running a tutorial at the NZ-NOG conference next week, so that should definitely get them started. The deployment that we have done, it's passed some basic tests for compliance that we've done in conjunction with the New Zealand Police. They've said that it did work. And in terms of the performance in our testing environment, I've managed to optimize things enough that OpenLI was coping fairly comfortably with 500,000 packets per second. So hopefully that would cover the use cases of most of the smaller network operators without too much issue. It doesn't cover the worst case if their customers are trying to DDoS themselves or others, then it might not keep up. But I do also have some ideas on how we can improve the performance there in the long run. It's just a bit more work, so I need to find a bit more time for that. But most important, the code's out. It's released. It's up on our GitHub, GPL3 licensed. We're more than happy for people to start taking a look at it, give us some feedback. It's still pretty early days, so mostly expecting sort of bug reports and a few feature requests from our users, but it would also be nice to see people starting to contribute that back and sending us some PRs as well. That would be great. We've packaged it to make it life a bit easier, at least for people who are using Debian and Ubuntu, right? And these are available from our bin tray, but we're hoping one day we'll get them into official Debian mainstream packages as well. That'd be cool. So there is one big question remaining, and we often get asked this, is how much support can an OpenLI user expect? And given how important the lawful intercept compliance is and how much is at stake, if OpenLI happens to fail at a key moment, it's a pretty fair question. So we've talked to people that have a wide range of opinions. Some people say they're going to need some sort of 24/7 support contract, right, for OpenLI to even be something they can consider. They won't be able to get it past the guys in suits. But the reality is that it's much more like the guy on the right. It's me at my desk putting in my best effort when I can, when I'm not swamped with something else. So we're still working through this, and I'm expecting it to be a pretty big discussion point at NZ-NOG next week, and we might have a bit more clarity then. And ultimately, I'm hoping to see a bit of a community start to grow around this software, where we've got some users who are starting to contribute back code, documentation especially, helping out with that, and user guides. Because, like I say, while everyone's network is different, there are also some things that they have in common. Maybe, if somebody's gone through the pain once, they might share their experience and save someone else the pain. Ideally, I'd like to see this sort of turn out like some of the other bigger open source projects in the networking space. So I'm thinking things like Free Radius and Bind and Asterisk, where they've got real communities built around them, and it's not just one guy dictating how things go. And it would really be nice to feel confident that we've got a bus factor that's more than one sooner rather than later. So finally, just a few quick thank yous. Our sponsors again, especially the technical people at those organizations who have been able to provide me with a lot of assistance, a lot of examples, and remind me of all sorts of things that I wouldn't consider because I'm a more academic person. I think there's a theory about how things should work, and the practice is entirely different. The New Zealand Police have been really helpful with this project as well. I'm not allowed to say that they support it, but there's been a lot of useful back and forth and help, especially in testing, and the New Zealand Network Operators Group as well for being so enthusiastic about the whole idea. So I'll just throw those links up again, but if I have some time, I'm happy to take a few questions. So the question was, can it handle a highly dynamic environment like a hotel where a person's identity is essentially quite tied to a room and a short time period, a few days? I honestly don't know. I think that would come down to how the operator is managing the identity. So whoever's providing internet to that hotel would be responsible for the LI rather than the hotel itself. So it goes a bit further up the chain. And then in that case, hopefully there'd be some way of being able to map the users within the hotel to say what addresses. Yeah, you'd have to have some sort of static mapping. Let's go over here now. Right, so the question is, if I can sort of paraphrase it, is that have we got essentially anyone from the ISPs or from the police contributing back to the project? And the answer is not yet. The hope is that at least from the ISP perspective, that as they're starting to use it and they maybe need to add a few extra custom features to make things work for them, that they might contribute those things back as modules or as optional components that people can make use of. Because, as I said, if it's a problem for one, it's probably a problem for someone else. It's not necessarily a problem for everyone. Simon? Yep. Yep. So I can tell you that for the last year, anyone who's had intentions of using this project has basically said, we're waiting for the project to be finished and released. And that's kind of been enough for them to get by, as long as they've been able to have some sort of alternative backup method. But that's obviously not going to be an excuse for anyone anymore. Yeah, so the question was, what consideration have we given to the risks of people who may not have such good intentions making use of this software? The answer is that to make use of this software really just takes a feed of user packet communications and turns them into the right format for them to be compliant with the law. And so if you have a feed of all of those packets, you can do whatever you want with that. Using my software is just a really complicated way to turn it into a format that you probably don't want it in anyway.
Essentially, the smaller operators being this subset of size of what kinds of operators.
Yeah, so the question is, do I have any insight into what larger operators have done, given that this is a project that's more targeted at smaller ones? The larger operators have, basically they've spent the money already. They went with the vendor solutions because for them, the economies of scale and all of that meant that it was just easier for them to spend the money and get the support level that they would get from those vendors because they're having to deal with the majority of the intercept requests anyway. And so they had to be compliant sooner rather than later.
Have you seen any outside?
We have seen some interest in adoption outside of New Zealand. So not that long ago, we got an email from a company in Kazakhstan who had somehow stumbled across our project and had said that their government is putting pressure on them to be able to do this sort of thing as well. So yes, there is interest outside of New Zealand. Once we get a few more sort of presumably deployments and things like that, and people sort of publicly saying, hey, this works, then I expect that could even rise further. But again, I think it'll always be quite something that will only really appeal to smaller operators. If you're big enough, then you're probably better off just spending the money and not relying on something I wrote. Anyone else? There's one there. Any tips on defeating it? Not that I can say right now while I'm being recorded, but maybe. Obviously, I know a little bit more about what can be used to defeat these things, and no doubt I still have plenty of bugs to fix as well. So there could be a number of ways to defeat it. I hope that we'll get better over time. But like I say, I'm probably not allowed to elaborate too much more on that. One more.
So you said you wrote C.
Yeah.
This seems like a particularly technical piece of software. I can see the code on my machine. You're going to process it in. There's also a system program that
Well, okay, so the question is, why didn't I basically use Rust? Because it's, yeah. So the answer to that is that A, I didn't have time to learn it. And the other one is that with the processing, obviously in terms of processing the SIP and the radius traffic, I'm going to have to parse that and look through that, and that is definitely a risk. The rest of the packets I basically just encapsulate, so they're not so much of a problem. And I really just have to be very careful about how I parse things and make sure that I don't screw it up. Hopefully with a few years of experience, I've got at least the obvious ones out of the way. But yeah, I'm happy that because we've released it, that gives people an opportunity to also audit it, people who are independent, and that will also help as well. But the real reason is, I didn't have time to learn Rust. Yep.